This is one of the driest places on Earth. Sometimes it feels like being on the moon or Mars.
During the day is a fantastic place, but during the night is absolutely astonishing.
So hi everybody, here we are. Welcome to the third edition of the Women of CTA event. First of all, thank you for joining us in this very special event. Special because of the subject, because of the date, but in this case it is also special because we are doing it for the first time live stream. So please bear with us if we have any technological problem or so on. Let me start introducing myself. I'm Alba Fernandez Barral. I'm the Outreach and Education Coordinator of the CTA Observatory, and I'm very pleased to be moderating this event in which we are going to talk with three amazing astrophysicists, with Elina, Mireia, and Leslie. They are going to talk about the work they do in the very high energy gamma ray astronomy field and also in CTA. But before we jump into this, before we delve into this extreme universe, into the gamma rays and so on, let me remind you that you can ask any question, curiosity, you can share your opinion and so on in the comments on Facebook and YouTube at any time of the event. At the end, after the talks, we are going to have a question and answer session. So we are going to gather all the questions you have. My colleague Megan, who is behind the scenes, she's going to gather them all, and we are going to cover them in this question and answer session. So please don't be shy. Say hi to us now there. Make a lot of comments, a lot of questions. We want to hear from you. We want to communicate for you. We are seeing already some comments where you're telling us where you're from. So we want to see from which country you are talking us. So keep commenting in Facebook and YouTube. Meanwhile, while you are tapping, I'm going to say hi to our speakers who are also in different countries. So let's say hi to them. Hi there. Hi, Leslie, Mireia, Elina, how are you?
Good. Greetings from Finland. Very cold here, minus 20 Celsius.
Minus 20. Is there any difference between minus 20 and minus 10 degrees?
Certainly. Minus 20, when you go outdoors, it kind of hurts your face. Minus 10 is great.
It's nice. It's a summertime. So thank you, Elina. Mireia, where are you talking from?
I'm talking from Spain, from Tenerife, kind of different place, and it's plus 20 or plus 15 degrees here, so much warmer.
Much warmer. So now I'm jealous. Here in Italy, it's not that cold, but I'm jealous now with you, Mireia. And finally, Leslie, you're in a very different time zone, right?
Yes, I'm calling in from Madison, Wisconsin. So good morning from the States.
Good morning, good afternoon to the rest, or good evening. So thanks a lot to you three for joining us in this third edition, for participating. We will talk to you later. We will make this the talks and the question and answers. But before, we are going to make an introduction to understand why we are doing this event, why we are doing Women of CTA. So I'm going to share my slides. Okay, here they are. So as I mentioned before, this is the third edition of the Women of CTA event. This is an annual event that we perform in the International Day of Women and Girls in Science. So today, in February 11th. This date was recognized by the United Nations in order to raise awareness about the gender inequity that we have in the science, technological, engineering, and mathematics fields, the so-called STEAM fields. and also to raise awareness about the underrepresentation of women, especially at the highest positions. We are going to talk about that. But what is the situation of women in science globally right now? So despite the efforts in terms of education that really help to increase the number of women in science, women are still underrepresented in some fields of science, as we are going to see in a few slides. And in generally, worldwide, women represent only 30% of researchers in the world. The problem is not only this low percentage. The problem is that we are losing women in each step of the academic career. So here you have a percentage of female versus male in the higher education, in a general scientific research career. So this is not considering only fields related to astrophysics, for example, but all science, including health science, natural science, and so on. And so here you can see that when entering the university, the number of women and men are quite equal. At some point, even women outnumber men. But after that, the percentage of women drop dramatically while moving forward in their career. So while moving to the PhD, to the postdoc, and to the research position, where we find this 30%. This phenomenon is well defined by the metaphor named leaky pipeline. So in the same way a pipeline that is broken loses water, we are losing women in each stage of the academic careers, in each stage of the system. So the system has to be broken somewhere. Another interesting concept that arises from this graphic is the so-called vertical segregation. When moving forward, when progressing in the career, the vertical segregation shows that one gender lacks opportunities or has less or limited opportunities to move forward. So in this sense, we can see this, for example, in science, in the fact that only a few women hold the highest position, the decision-making positions. To give you an example, in the European Union, they published in 2013 that the number of female directors of tertiary institution and university was only 60% and 10% respectively. So we can see that there is a glass ceiling, there is something that women need to overpass, that makes difficult women to hold these highest management positions. And not only in the academia, but in general, in the highest stage, for example, with the Nobel Prizes. So far, only 24% of women were awarded with the Nobel Prize in a scientific discipline, only 4 in physics. While these 24 are extremely important, they barely represent 3% of the total Nobel Prizes in science. But let's look to a positive side. There are some good news if we look to the regional level and to the national level. So to the regional level, we can see UNESCO published that since 2016, already some regions reached this gender parity in terms of percentage of researchers. For example, Central Asia, and also some parts of some regions of the Latin America. At the national level, they published that 30% of the countries out of 126 that provided data already achieved this gender parity, which is a really great accomplishment. But we cannot relax. Even these countries have other problems. For example, this vertical segregation, the fact that we have few women in the highest position, it's also happening in these countries or in these regions. And of course, at the region level, we can see that we still have a lot of regions where the gender equity is very far away. Another problem that we are facing in this field is that only 30% of female student population choose STEAM-related fields. And it is even worse for the most technical fields, those that are actually related to astrophysics, like physics, mathematics, engineering, computational science, and so on. They are among the least chosen careers in STEAM by women. This is the so-called horizontal segregation, when an area of study is dominated by one of the genders. And this is a problem, especially for the technical careers I mentioned before, like physics or computational science, because besides this horizontal segregation, we have to add the leaky pipeline that I mentioned before. So we end up with really few amount of students at the beginning, and so we end up with really few amount of female researchers at the end. So this means that we still have a lot of work to do ahead of us. UNESCO show in their program that there are gender differences in STEAM education participation that affect girls even before the primary levels. Also, girls are losing interest in the STEAM subject with the age. To prevent this, it is actually very important, the female role model, including the teachers in STEAM. Also, as we see here, as we saw just now, there is a gender gap in STEAM in the higher education. Women tends to select STEAM careers less, only 30%. And it is even worse in these technical careers. And which is even worse, women leave these disciplines in a higher number than their male colleagues. This is different from one country to another, as we just saw. So it is related to the culture, to the gender stereotypes, such as the family duties assumed to women, etc. Actually, these gender stereotypes are some of the reasons why girls do not want to pursue these STEAM careers, because they are heavily influenced by the socialization process and these stereotypes ideas. So this is why we are doing this. This is why we are doing Women of CTA event, to collaborate internationally, to raise awareness about this gender inequity in science, to raise awareness about the underrepresentation of women, especially at the highest positions, and to show that there is a lot of female role models in science, like Elina, Mireia, and Leslie. So, as I always say, let's celebrate the International Day of Women and Girls in Science today, so we do not have to celebrate it in the future. And with this, I want to thank you again for joining us in this event. And I hand it over to Elina, who is going to be our first speaker. Hi, Elina.
Hi.
So I'm going to introduce briefly Elina. Elina, she's a senior researcher in the University of Turku. She specializes in the mission models of blazars, which are one of the most extreme sources in our universe. I think Elina is going to talk about that. Elina is actually now the science coordinator of CTA. So whenever you want, Elina, all yours.
Okay. Hello, everybody. So thank you for the nice introduction, Alpa. So I'm going to talk about jets launched by supermassive black holes, and also about kind of how my journey on or the interest on these extreme objects came about. So as I said in the introduction, I come from Finland. And Finland, if you don't know anything about Finland, you still might think that it is an extremely cold and dark place, and you are completely right. The good thing about the darkness or the very, very long nights during the winter is that you can see stars also not just during the night, but in the early evenings. And already when I was very young, I was fascinated by the night sky. I guess most of us are. but here in the darkness was very easy to see. And when you look at the dark night sky, you don't have to watch it very long when you start to, especially if you are in the dark place. And again, Finland mostly is dark place. If you're in the dark place, you start to spot that there is some kind of a pattern there, going some kind of path, like somebody would have put milk on the sky. And that's, of course, our own beautiful Milky Way that you can see in this picture. And this fascinated me, of course, as a child. I watched the sky, but I also did read a lot of books about astronomy as soon as I learned to read. And from those books, I then learned that this fuzzy pattern in the sky is actually our own home galaxy, Milky Way, formed by 150 billion stars. And it actually, if we could fly outside of it, it actually has this kind of beautiful spiral arms that you can see in this picture. It also started to interest me a lot. What is there in the center? You can see that it's bright. There must be a lot of stars, but what is there very much in the center? I, of course, started reading about that as well and learned that we really cannot see there. There is so many stars that it's not possible to see it in the terms that we usually understand as seeing. So we cannot see it in the range of visual light. But astronomers, of course, know how to get away or get around that problem. So if you cannot see through it in the visual light, you can try to look at X-rays, or especially in the infrared, when you can see through the dust very efficiently. And when astronomers did that, they see this kind of picture of the central region of the Milky Way. And there, very, very close to the center is this very, very dense region, which in the X-rays looks like this. And we now know from the very extensive studies of the infrared observation of the stars circulating around the central region, we know from their tracks that there must be a supermassive black hole. And this is, of course, super exciting. I do talk a lot about black holes in the schools for children, and I'll tell you more about that towards the end. And black holes, I mean, what can be more fascinating than black holes for children? Of course, the only thing that can be more fascinating is supermassive black holes, and that's what we have in the center. However, for a very, very long time, we thought that enormous supermassive black hole that we have in our Milky Way centers is just sleeping there. It's not doing much. Seemed to be like this kind of a dragon from the stories that you read when you are a child, that the dragon is sleeping somewhere inside the mountain and never comes out. We know that there is a dragon in the center of the Milky Way, but we thought that it doesn't really do anything there. Until Fermi Gamma Ray Telescope was launched. So we thought that our black hole has been sleeping, our own supermassive black hole has been sleeping for at least millions of years. But when we then had the possibility to look at the surroundings of our galaxy with Fermi Gamma Ray satellite, so again, a new way of observing the universe, gamma rays instead of just near infrared and X-ray observations, which I was talking about just before, it revealed us this kind of very, very strange, huge bubbles around our Milky Way. And I guess this figure needs some kind of little bit explanation. So this plane here is our Milky Way. So it's formed of 150 billion stars. So it's enormous structure. So now if you compare these huge bubbles that the Fermi Gamma Ray Telescope saw, you can see that they are enormous on size. They are larger than the galaxy, or the same size of the galaxy. Now we see them in the gamma rays, so it means that they must have formed very recently, because gamma rays are extremely energetic emission, and particles that can emit gamma rays, of course, live very short, because they are very energetic, so they lose their energy and they cool down. So this feature has to originate from some rather recent activity that is most probably triggered somehow by our supermassive black hole that we thought that would be just sleeping. This is kind of very nice demonstration how we'll usually learn something very unexpected. This is not what the Fermi was launched for. This is not what we expected to see when Fermi was built. But when you get kind of a new, much more sensitive visualization of the universe, or better tools to observe universe in the new energy regime, this is what you get. So you get you might get something you did not expect, and that's of course why astronomy is so extremely fascinating. Now, moving towards to my own research, we know that actually most of the galaxies do host a supermassive black hole in their center. And in some active cases, these black holes actually launch supermassive, super relativistic jets. And these jets launched by supermassive black holes are the most efficient particle accelerators in the universe. And this is my research field. This is what I'm studying. So these jets, they are extremely efficient particle accelerators, which means that we can see them in the very highest energies, and those very highest gamma ray energies is what CTA is going to observe. And when I started to do my master's, we knew in the very high energy gamma ray regime, we did know 5 of these relativistic jets that had been observed in the very high energy gamma rays. Throughout my master's and PhD studies, one of my main interests was to try to find more. So finding and triggering observations to look at the flaring AGNs. So these are called AGNs and blazars sometimes as well. And discovering more and more of them was actually a very crucial part of both my PhD and postdoctoral research. We nowadays know almost 100, and some tens of them originate from the observational programs where I have been very closely involved. Now, as mentioned, these blazar jets are extreme particle accelerators. And as a physics student, I was, of course, always very interested in particle physics as well. I mean, it's fascinating. There is particles that we cannot see, and especially fascinating have always been so-called ghost particles, so neutrinos. So we know. So the image here is from Super Kamiokande, which is a neutrino observatory. And this is an image of our own sun, but taken in neutrinos. And we know few neutrino sources in the sky. So we know our sun. So in this figure, you can see the neutrinos from different energies, and sun is one source there, around in the MeV range, so mega electron volt range. Then there was an observation of a supernova burst from 1987A, and that, by the way, I was not in university back then yet. I was still in elementary school. But that's it. It's 2 sources until very, very recently. So it's our sun and then this one single supernova. However, in not so just a few years ago, when IceCube came online, so IceCube Neutrino Observatory at Southern Pole, they started to see extremely high energy neutrinos, observe extremely high energy neutrinos, which could not be of atmospheric origin, which is this component here. And these are then called astrophysical neutrinos. However, their source was unknown, so it was definitely not known what astrophysical sources would be emitting. Where are these neutrinos of very high energy originating from? Of course, extremely good candidate sources are these the most extreme particle accelerators in the universe, so the blazar jets. And in 2017, we actually detected a source which emitted a neutrino, detected by IceCube Neutrino Observatory. And then on the same time, it was emitting extremely brightly in the very high energy gamma ray range. And with this, we then concluded that it is very unlikely, it's rather unlikely to happen by coincidence at the same time, and that this blazar is the likely source of this extremely high energy neutrino. So that would be the first known source of this extremely high energy astrophysical neutrinos. But even if we now might have this one source, and even if we do know almost 100 very high energy gamma ray emitting blazars already, I would still use this nowadays too much in science used tip of the iceberg metaphor. I'm pretty sure that we know only the tip of the iceberg of the very high energy gamma ray sky. So there is plenty of everything to reveal from there. And Fermi has also very nicely, Fermi's gamma rays telescope has also very nicely demonstrated to us that when we observe something with better sensitivity than with ever before, we should always also expect to observe something, expect the unexpected. And this is, of course, where the CTA comes into play. So I cannot describe how much I'm looking forward to our first observations with the CTA. We have already great observations from the prototype telescopes, and I cannot even guess what we will see when the full array will be there. But I would like to tell you, however, already that CTA already, even if it has not started the full operations, has had quite some effect on my life. And to tell you about that, I actually have to look back to my career a bit, or to explain that to you. I need to look back of my career a bit. And I would like to start that by showing this picture of myself and my friends on the last day of high school. So here you can see we are ready to be scientists, all four of us, with our green hair and kind of stereotype as scientists to be. Immediately after the high school, I moved to Iceland, and as unlikely it sounds, Iceland is actually, the University of Iceland is actually the place that introduced me to the gamma rays. So my first supervisor there, Gunnlaugur Björnsson, was studying gamma ray bursts, and I was immediately fascinated by this phenomenology, which we didn't know so very little about. So that was already in my very first years of university studies. Then I moved back to do my back to Finland to do my master's and PhD in university, or to finish my master's and then start my PhD in the University of Turku. And this is a picture of me from my PhD defense. Not sure that everything I've written there is correct, so don't look that too carefully. But I wanted to share with you the picture from the party that we had after the PhD defense. This is me and my family. So by the time I did have my PhD, I already had 3 children that you can see here, and I guess that's not very common. It's definitely not very common in Finland, and I also know it's not very common thing in the other parts of Europe. And I would not say that. I mean, I usually do not like to give any advice about this, but I just want to tell you that this was the situation when I did do my PhD. So in the end of, usually when you finish your PhD, you move somewhere abroad to start to do your first postdoc position, and then maybe a second one again in another country. And with 3 kids, I somehow felt that was really not the option, especially because only 2 years after my PhD defense, I then also had the 4th kid. So I somehow felt that this is not for me. However, in the scientific career, it's very, very important to get some international experience. And this is certainly something that first, the Magic Collaboration in this picture, this is from the first meeting of Magic Collaboration where I participated from 2002, actually. I'm there in the back row. And then later CTA consortium has played, I'm here, has played extremely important role for me. So I have get this great opportunity to talk and work with many people from many different countries, which has given me a lot of international experience, but of course also very many international friends, for which I'm very grateful, but which has also benefited a lot my scientific career. And I would like to finish my presentation by highlighting that science is for everybody. And this is something that I try to keep in mind in my daily life and also in my working life. And this is one of my main motivations to do a lot of outreach work. So here is some photos from the time before COVID. So when it was actually nice to work with children on the local science center. Here we have built some water rockets. Here some experiments with liquid nitrogen. Here we are launching, or I'm just observing this one. But here we were launching with this kind of huge balloon, KitSat, to high in the atmosphere, and then we were tracked. So this is with high school children. Then we were tracking it with the laptop. And I have always had also a great interest in teaching astronomy using planetariums. So I have been also very active on that. And now in the times of endless Zoom meetings and live stream events, I will actually do my first remote school visit tomorrow. And I was sent a lot of questions by the 10 years old about black holes, and I look forward to talk to them. And thank you.
Thanks a lot, Elina, for sharing your experiences and for introducing us to these super interesting astronomical sources. So don't forget, everybody, you can ask Elina any questions in YouTube or Facebook. We will answer them in the question and answer session. So thanks, Elina, again. We are moving now to Mireia.
Hi, everyone.
Hi there. So I'm going to briefly introduce Mireia too. She started in this field in the very high energy gamma ray astronomy in 2013. She's been a collaborator in different international consortiums and collaborations like MAGIC, Veritas, and of course CTA. In physics, she focused on active galactic nuclei, so also in extragalactic sources as Elina, and she was also focusing on software development that I'm sure she is going to talk about now. So whenever you want, all yours.
Yeah, thank you for the introduction, Alba. So as Alba said, I will also talk about active galactic nuclei, AGNs, and blazars in particular. But I want to start with something a little bit different. So that has been my one of the topics that I have been focusing lately, which is a more technical aspect of gamma ray science. And let me begin by showing you why we care about Cherenkov telescopes. So here you have a picture of the electromagnetic spectrum, and as you can see, the visible light, what you see with your eyes, is only a tiny fraction of the energies that radiation can have. And unfortunately, we cannot see all this radiation through the atmosphere. In fact, the atmosphere is opaque in infrared, for instance, X-rays, ultraviolet, gamma rays. It only allows to pass a small fraction of it, visible light, and also in radio. So in the energies or wavelengths in which we don't see anything through the atmosphere, that we cannot look up during the night, we need to do something else. And what people usually do is to send satellite with telescopes, no? And we do that in infrared, we do that in X-rays, we do that in gamma rays. And why, if the atmosphere is opaque, why do we install Cherenkov telescopes, which are gamma ray instruments, on Earth? The reason is very simple. Several decades ago, people figured out that we can actually use the atmosphere as a gigantic detector, as a gigantic instrument to measure these gamma rays. And that's something that for me was fascinating when I was studying my master thesis, my master studies, and would kind of make me decide to continue my research career in this topic, in gamma ray astronomy. What Cherenkov telescopes do is to observe gamma rays when they hit the atmosphere from above, coming from a distant source, like a the environment around a black hole or some compact object. When these particles travel and hit the atmosphere, they start producing a shower of secondary particles. So this initial gamma ray generates electrons, positrons, and through a lot of different processes, this in turn generated some kind of flashes of light that we can observe from Earth, from the ground. And these showers, what they have in common is that they are super short and they are very dim, so you cannot observe them with your naked eyes. You need some kind of special telescope to observe that. And these telescopes are these Cherenkov telescopes, like CTA, and they are composed by large mirrors in order to gather a lot of light, and then very, very, very fast cameras. Imagine that you have to picture something in just a few nanoseconds. That's really fast. So this is one of the images from one of these telescopes of a gamma ray event. As you can see, these images are not very fancy. They don't have a very high resolution like your compact camera, but we still can do a lot of things with this. But in order to get that, so from our telescope, here you have an example of a Cherenkov instrument, a Cherenkov telescope. You get these images or videos because we take a lot of images per second. And how do we get into science from here? Well, the first step is to do some proper calibration of your instrument. You need to convert these fancy pictures into something that you can measure, that you can do something with. And this calibration is not static. It's not something that you do once and you forget about it. But since these telescopes are usually installed in very remote places, like high mountains, very close to deserts, in order for the environment to be dry enough and have clear nights, these telescopes are subject to a lot of atmospheric phenomena, like sandstorms, Kalima in the case of the Canary Islands, because we are very close to the Sahara Desert. But also, since they are in high mountains, you have winters, and the telescopes might even freeze during the night. And that here you have a picture of a beautiful picture I took of Magic one night in May, that it was actually frozen. So you have to monitor the behavior of these telescopes. In addition, you need to take into account that these telescopes don't have domes like normal optical telescopes. That would be too expensive for the requirements we have of fast movement and etc. No? So you have to really be careful with the monitoring of the performance of the telescopes. The telescopes get old, mirrors get replaced, cameras get upgraded, etc. So you have to continuously calibrate the instrument in order to convert these funny images into science. And that's something I have been doing in the last few years, particularly with Veritas, but there is a lot of people who are doing this and trying to guess what are the best techniques and methods to do this with other instruments like CTA. But let's imagine that we have our telescopes calibrated and we can actually do science. So what kind of science can we do with CTA or any other Cherenkov instrument? Well, we can observe many objects in the sky. From sources that are inside the galaxy, like for instance pulsars, which are rapidly rotating neutron stars. We can observe the residues of explosions like supernovas, supernova remnants, for instance. We can see the Fermi bubbles, as Elina was pointing out. We can see binary systems in which we have a black hole, for instance, and a massive star that is being eaten alive. But we can also go farther away and study sources that are outside our galaxy. And just to remark some, we have other galaxies as well close by that we see some gamma ray emission, and we think that it's coming from the same sources that I was pointing in the previous slide. We can see some explosive phenomena like gamma ray bursts when there's an explosion linked to a compact object. Or we can see active galactic nuclei that Elina explained to you, that it's composed by a gigantic black hole in the center of a galaxy that is sometimes powering very huge jets that have sizes comparable to the size of the galaxy. So let me try to summarize how these AGNs are formed. So imagine that you have the compact object, the black hole, and it's accreting material that is falling, forming an accretion disk here. Sometimes you even power some particle accelerators that are in form of jets that can emit radiation in many energy bands, in particular gamma rays, and this really get far away. So the sizes are comparable to the size of the galaxy. Unfortunately, when we study AGNs and when scientists do their science in different energy bands or looking at different aspects, we can only see a tiny fraction of what AGN are. So this slide summarizes a little bit of this effect. If you are looking to an elephant from very close by, you will only see either the head, a leg, or the body of the elephant, which will look like a wall, an enormous wall. So you don't see the entire picture, and you don't have a feeling of what's really going on that source, no? So let me go back into AGNs. An important aspect of these sources is that the geometry plays an important role. In fact, if you look from the side of these sources, you will see the accretion disk, of course, and these jets going far away, forming some kind of lobes, and we call these sources radio galaxies. And people started to study this very long time ago, and they realized that these sources emit in many energy bands, like radio, X-rays, etc. And but of course, if you go to other geometries, like more face-on, then you see something that looks a little bit different. And in fact, if you go to the extreme case in which the jet is aligned towards you, then you don't actually even see in many cases the galaxy itself. You only see a bright flash that is outshining everything else. So when people started to study these sources, which are called blazars, or in the case that they don't have these radio lobes, they will be called quasars. What people saw was a point-like source. They didn't see any kind of a structure or anything else. So they didn't know what was the nature, even if these sources were outside our galaxy, no? So that was interesting to discover that these sources are actually just a tiny fraction of the entire galaxy, no? But the brightness is so high. Of course, with gamma rays, we have not that fancy pictures. We have a very limited resolution. So this is kind of an image taken with Fermilab of a small fraction of the sky. And as you can see, our sources look like points. They look like small blobs there. But what is interesting about AGN in this energy regime in particular is that they are very, very variable. So they change a lot over time. And in this picture, for instance, I'm collecting more than 10 years of data taken with this Fermilab telescope in the space. But it will be very similar with Cherenkov telescopes. So as you can see, there is nothing in the center. And then suddenly in the last few years, there was some kind of activity from this blazar, this PKS 1441. And this is telling you that something is really happening either in the disk, in the accretion disk, or in the jet. So that has to do a lot with particle physics, with something that is accelerating particles and then producing this gamma ray emission. And scientists do that, do like these things, and they like to study them not only with gamma ray telescopes, but also in other wavelength bands. For instance, here, this is how this science looks under these nice pictures. And you can see here the brightness of this object in several bands, no? And you see that it is changing a lot with time. But you can also do other things with blazars. Blazars are things that are very far away, and they are launching to you gamma rays. These gamma rays can, in fact, interact with something that we call extragalactic background light, which is a soup of radiation that is filling the entire universe. And it's very interesting for us because this soup of photons is encoding very important information about how stars are formed over time, what is the history of the universe, how galaxies were formed together, etc. No? So we really want to understand how this radiation, like what is the intensity of this radiation. And we use these blazars. So when one of these gamma rays interact with one of these photons from this soup, the gamma rays absorb and we don't see it anymore. So by studying how these gamma rays disappear from our sight, we can actually infer what is the intensity of this soup of photons and in fact reconstruct the history of the universe. And that was another of the aspects that I love the most about this field, that you can actually do the cosmology, study the history of the universe and try to understand how things are formed, how galaxies are formed, how stars are formed, how were stars in the past, etc. I studied this during my master and then jumped into it by kind of accident during my thesis, and then I fell in love with it, and I have been working on this field during my career. And just to finalize, gamma rays, as I was trying to show you, can be used for many things, from particle physics, trying to understand the interaction between these gamma rays with the atmosphere, to develop instrumentation and to work on electronics. And this has to do also with medicine. These instruments, these cameras can be used somehow for medicine to treat tumors, for instance. And it has also to do with astrophysics, of course, because we are studying different kind of sources. And finally, it has to do with cosmology. We can study the history of the universe. And I think that's a little bit of the summary of why I find this gamma ray field interesting.
And now we find it too. Thanks a lot, Mireia, for this super clear and interesting talk. Thanks a lot. So we are going to come back to you with the other speakers in the question and answer session. There are already a few questions in Facebook and YouTube. Let's move now to our last but not least speaker, Leslie.
Hello.
Hi there. Hi. So Leslie, she is a graduate student at the University of Wisconsin-Madison, where she is performing the PhD in the CTA group. Her work is actually focused on hardware, developing the camera of one of the prototypes telescope for CTA, the PSCT, that she will talk about right now. She worked on the installation of this camera and also led the first light observations and the observations of the Crab Nebula that resulted in the detection of this standard candle source in the gamma ray astronomy. So, Leslie, I hand it over to you.
Thank you so much for that introduction. As Alba said, my talk is mostly about hardware, because that's what I work on the day-to-day. So I hope that after this talk, you'll know a little bit about me, a little bit about the project that I work on, and also just a little bit about the work that I do on the day-to-day. So to start off, a little bit about me. So before I was a graduate student at UW-Madison, where I am currently, I grew up in Alpine, which is a small town, like 40 minutes outside of San Diego, California. I did my undergraduate at UC Berkeley, so go Bears. And actually, before I became a graduate student, I worked as a high school physics teacher for a year in Pittsburgh, California, not the other more famous Pittsburgh. That was a wonderful experience. I worked there for a year before I applied to graduate school and came here. So during my time at UW-Madison, I've been involved with a couple of groups that are really important to me, that I think really made my graduate school experience something amazing. The first is the Gender Minorities and Women in Physics group. So you can see a couple of our events there. Some of them, like the top photo, are just for fun times, getting to know other women in the department, and making sure that there's a support network for us there. And some of them are more educational. The bottom photo shows an outreach event that we did through GMAWIP. So it's always an opportunity as well. The other organization is the Physics Graduate Student Council, which is focused on making sure that graduate students are supported here at UW-Madison, and that has gone a long way toward making me feel welcome, and hopefully I can make others feel welcome as well. So now on to the project. So a little bit about CTA for those of you in the audience that maybe don't know as much about the project. It's a telescope array, so groups of telescopes at 2 locations, one in the south and one in the north. There are 3 telescope sizes, and each size focuses on a different energy band. So the smallest telescopes are looking at the highest energy gamma rays, the largest at the lowest energy, and then the medium-sized telescopes are looking at this kind of core energy range. And the telescope that I work on is a prototype candidate for this medium-sized telescope, so that's what we're looking at. The telescope that I work on is a little bit different than other telescope designs, so I wanted to kind of go over that. Mireia did a really good job showing a bunch of photos of the single mirror design, which you can see on the left-hand side. This is called a Davies-Cotton or single mirror telescope. And basically, you can see the light comes in and it bounces off of one mirror and then is focused onto the camera. The telescope that I work on, the PSCT, is a double mirror camera. So what that means basically is that the light comes in, bounces off of one mirror and then a second mirror and then into the camera. So you can see the difference between what the 2 telescopes look like. Both of these telescopes are near each other. They're both in southern Arizona. And if you look very closely in this Veritas single mirror telescope, you can see the reflection of the PSCT. So that's how close they are to one another. So a little bit more about the PSCT. So the 2 mirrors have a couple of advantages. The first is that the telescope can be more compact, and it has a wider field of view, so that means it can see more of the sky. The mirrors are a special shape that are pretty difficult to produce, but they are optimized for maximum resolution and field of view, so they help a lot with those advantages. In order to take images with this telescope, we need a very fast and very high resolution camera, and that's what I work on. This is possible through new developments in SIPM and ASIC technology. So a little bit more about the camera, which is the part of the telescope that I work on. So down here, you can see a kind of representation of the PSCT, the two mirrors, and then the camera goes right in between them here. When you look face on onto the camera, you can see the focal plane, which is basically the surface that's taking images. And right now, only this central sector is installed. And you can actually see a photograph of that over here. So keep this shape in mind. It'll come up again later in my talk. And this is instrumented with modules. So when the modules are out of the camera, this is what they look like. So they slide in from the front, and then they you can see the back of the camera over on the right-hand side. So they slide in through the front, and then they plug into these back-end electronics on the back end. The camera was shipped to the Fred Lawrence Whipple Observatory in southern Arizona in 2018, and this is us unpacking it. So you can see kind of the scale, the size of this camera. It's pretty big. So once it arrived at the Fred Lawrence Whipple Observatory, it was time to lift it up into the camera. But a little bit more about on-site, because it's very interesting. I love it there. I actually just got back from a month-long trip. So as Mireia said, our telescope is in a very hot, dry climate in the desert. And this is helpful for a variety of reasons, but it also means that it's kind of an experience going out there. Right here at the bottom, you can see a picture of the dorms that we stay at when we're on site. So they're quite remote at the top of a mountain. And this picture, which is sadly the best picture that I could get, is of the local wildlife. This is called a quadamundi. It's kind of like a long raccoon. And there's plenty of wildlife out there. It's very far out of the way, so it's very fun to go out there. Some things that I love about being on site is all of the hardware work that I get to do while I'm there. So I am certified to go up on a man lift. You can see it in a couple of photos. And I do most of my work on the telescope up in the air like that. We also have our collaboration meetings out at Fluo often. So you can see pre-pandemic us having a good time one of the evenings of our collaboration meeting. Okay, so back to the hardware and how we install and commission this camera. So on the very right-hand side, you can see the setup of how we are lifting the camera into the telescope. This was done with a very large crane, so large, in fact, that I had a tough time getting a photo that got the whole thing in there. Basically, we lifted the camera on these straps, and you can see here, right through the center of the telescope, I'm actually this person right here attempting to help lift it. We'll lift it straight up and then install it right here into this little kind of cubby. Once the camera was installed, we had to put together and install the modules as well. So you can see a photograph of me a long time ago when my hair was a lot longer, assembling the modules as they were shipped, disassembled, so that we can install them into the telescope. Here you can see a close-up photo of how those modules slip into the camera. So they just slide in, and then once they are all in together, they create this nice flat focal plane. A lot of the work that I do on site is hardware, and honestly, I love it. So one of my favorite projects was the waterproofing of the camera, and you can see here all of this white stuff. That's the waterproofing material that I used. So how that went, I was in the telescope, in the man lift, for 8 hours a day for a couple of days, get great cell phone service up there, listen to music, waterproof the camera. It was a really good time. So science is just as much about the hardware as it is about all of the data analysis, and it can be really fun. Okay, so once everything was installed and commissioned, we began with observing. This was kind of a long process. So the photograph in the center here is a photograph of the inauguration of the telescope, which happened in January of 2020. And then very briefly thereafter, we had our first light. So that just means that we turned the telescope on, pointed it at the sky, and just figured out if we saw anything. And this little movie here can show you what that looks like. So this was our first light, and I led those observations. After a year of commissioning, I went back onto site in January of 2020 and took observations of the Crab Nebula. And you can see here one of those images, which is our first confirmed gamma ray event from the Crab. And these observations led to the detection of the Crab at a significance of 8.6 sigma. For me, so in addition to leading these observing runs, I also was able to establish the observing procedure and create an on-site manual so that people after me can also observe with the same telescope, which is always a good time. And finally, a big part of what I do day to day is communicating science. So whether it's through something like this, or maybe through a conference like ICRC, it's always really important that we can communicate what we're doing to others so that everyone's on the same page. One of my favorite things that I did was a Girl Scout talk. So I gave a talk through the Gender Minorities and Women in Physics group to a local Girl Scout troop to help them get their science astronomy badge. So that was really fun. And it was a good time. They had great questions. So it was always fun to talk about my work in that way. Okay, thank you.
So thanks a lot, Leslie. It was a super interesting talk discovering this telescope and your work. So I'm going to invite the other speakers, Elina and Mireia, so we can start the question and answer session because we have a few questions already in the comments in Facebook and YouTube. So let's see. Let's start with one for Elina, for example. I don't know if we can see them in the screen. Otherwise, I will read it directly. Okay. Okay, here it is. One from Jim in YouTube. He says, he questioned, is there any gravitational waves corresponding to high energy emission or neutrinos? This is for you, Elina.
This is an extremely interesting and good question. Thank you. So it's commonly, so when we discovered the first gravitational wave signals, there was a lot of these discussions that we have a new sense for the universe, and it was described that, you know, if we only when we are only observing electromagnetic light, electromagnetic radiation, it's like it's the vision, and then the gravitational waves is the lets us hear, and then the high energy neutrinos is then the third sense. I don't know if that's the taste or the smell, not sure. But up to now, we really don't know any event which would have emitted. I mean, it would be therefore of great interest to have one event where we could observe all three of these. One event where we could use all of our senses that we know up to now, but up to now there is none. So we know this one gravitational wave event where we did then get an electromagnetic radiation from all the way from radio to X-rays, but no neutrino emissions from that. Then we have the event which I described, where we had the high energy emission and neutrinos, but the combination of three not yet there. Hope to see it in the future.
So let's see if we got one with CTA.
That would be great.
Okay, so let's move to another question. This is clearly for Mireia. One in YouTube says, my question is, what questions can have EBL told us about the history of the universe? And what future questions can CTA tell us about the cosmology of the universe?
Okay, so that's kind of a tricky question, but let's try to get into it. As you know, if you look farther away, you are looking somehow more back in time, no, to more ancient times. And of course, the universe have evolved during this time, and stars have been being formed at different rates, and different kind of stars were formed, no. So EBL, I was saying that EBL collects all this starlight from the early universe into our times, but what maybe was not that clear is that because blazars can be found at different distances, the emission that we see from blazars, these gamma rays that are coming from these blazars, are coming from different times somehow. They are coming from different distances, so they are coming from different times. So the universe that these gamma rays see, this soup of photons that they see, comes from different times. So by studying blazars at different epochs, at different distances, we can somehow take slices of the universe, take slices of this soup of cosmology somehow, and study it at different times. And that's something that we have been trying to do by collecting enough blazars at different epochs, enough blazars at different what we call rev-seed, which is the look-back time, and trying to calculate what is the intensity of this extragalactic background light. And then we can reconstruct how much light was in the universe in this EBL. And that has to do with the amount of stars that have been formed already. And this tells you, for instance, that in these star formation rates, the speed of formation of stars has changed a lot, and it had a peak at some point, and now the universe is somehow slowly dying. So now it's forming less and less stars over time. But that's not the only thing that we can extract of cosmology or fundamental physics with Cherenkov instruments. People look also into other things, like, for instance, gigantic intergalactic magnetic fields. So we know that there are some magnetic fields that are exist in the universe. And this somehow, when for instance, when a gamma ray travels and interacts with the EBL, I was telling you that it disintegrates, producing pairs of particles. Well, these particles, since they have charge, they can be deflected, and this deflection happens because there is a magnetic field. So you can actually study, infer the intensity of that magnetic field that is filling the space between galaxies by studying the EBL, for instance. And there are also other aspects about fundamental physics, like studying if the light propagates at the same speed at different frequencies, for instance.
So this is super interesting. We need to do a lecture only on this. We have to do it in the future in a webinar or something. So thanks a lot, Mireia. So let's see another question. Another for La Letra. Sorry if I did not pronounce correctly your name. Also in YouTube, how often do the technical team have to go on site and do observations need to be done on site? Or can they be operated remotely?
Yeah, so it kind of depends on what we're talking about. If we're talking about commissioning of the telescope, I go on site very often. So this time last year, I was in Southern Arizona for a period of 4 months. I was also in Arizona for all of January, kind of working on getting the telescope ready for observations. Once we are actually observing, we would probably need someone to be on site approximately 3 weeks out of the month. It depends on local like considerations. But the fact that we can operate remotely, that is something new. Like many projects, we were affected by COVID-19, and we kind of had to figure that out over the course of the last year. So while we can't run completely remotely, we do have procedures in place so that we can have fewer people actually on site, and then they are supported remotely by remote observers. So that has been kind of a new thing, but very helpful and very interesting.
Thanks a lot. I think we all went on shift, and it is really an experience being on the observatory working with these telescopes. Okay, so this one is for all of you. By Susanna says, what do you like the most about being a scientist? This is nice. So whoever wants to start, Elina, maybe?
Yes, oldest. It's actually a not simple question, because there is so many things that I actually like. Some days I think that I actually would like most to be proven wrong, because that's actually then, you know, then you have a very definite answer to something. So we very frequently we work on building a theory, which we would like to, of course, with the idea that we will be, you know, what are we going to see? We make a prediction and we expect to be right. But it's actually would be equally interesting, if not more interesting, to be proven completely wrong. So that will be my answer.
That's an interesting one. That's an interesting point of view. So Mireia, for you, what do you like the most?
Maybe to get to work with different teams in different countries, for instance, and see how people can have different answers for the same questions. For instance, I remember when I was working in MAGIC, I mean, there was some ways of, for instance, in the calibration that I was mentioning, of doing things. And when I moved into the Veritas collaboration, that changed a little bit. So people had different ideas, different solutions to get around some problem, no? And that's very enriching, and you can actually learn a lot of these different ways of thinking, no? For me, that was very enriching.
This is one of the reasons why diversity is so important, because it really helps the creativity and it's beneficial for the working environments. And Leslie, for you?
Yeah, I think that it's pretty obvious from my slides, but my favorite part is being on site, working on the instrument, and taking observations. Part of that is, like Mireia said, I get to meet people from all over the world, get to talk to people who I never would have been able to meet had I not been working on this collaboration. But also just taking observations is a very, I don't know, mind-bending experience. You really feel like you're touching the universe. You can see these gamma rays as they are coming in, and it really makes you feel connected to the science and kind of what's happening out there in the universe.
I love that. Okay, so I think we are going to finish here the question and answer sessions because we are a bit delayed. So I would like to thank again all of you for these amazing talks. It was extremely interesting knowing more about your work and knowing more about your experiences, professional and personally. I would like also to invite Megan, who is behind the scenes and was organizing all these. Here they are. Hi, Megan.
Hi.
Okay, and with this, we are finishing the event. thanks a lot for everybody for joining us in, as I said, this very special event for us, Women of CTA. And see you in the next event next year, or in the next event we do in CTA. So have a look to our social media and our website and stay tuned. So bye.
Bye, everybody.
Bye-bye.
Thank you.
Thank you.